Hello everyone, welcome back to another discussion on a chapter for TMUA/ESAT. So today we'll be looking at derivatives. Now I'm doing these reviews in no particular order because I have a regular class with students, and whenever I feel like the notes are up to scratch and they are worth revealing to the wider audience, then I do one of these chapter reviews. So we are doing derivatives today, and the syllabus on derivatives is quite less. Like on the official handbook, you will find like 10 pages worth of study material, which is literally quite less because if you dive into the world of calculus, there is an entire course AP calculus on this particular section of calculus. All right, so you will have like 7 8 chapters on derivatives and so on. Now what is there in those syllabi which are not present here? Now this syllabus is highly condensed, so there are certain things that they assume you know, and then there are certain things they just hint at, like a student should be able to do this. All right, so we will look into all those theoretical concepts. Now I'm not that bothered about the rules of derivatives, about the different formulae of derivatives. I assume that you have studied that in school. If not, you can look it up on the internet, you can look it up on YouTube. There are a lot of quality lectures. You will find how to derive the rules of derivatives from first principles and so on. There are a lot of chapters that have been leading up to this section, and none of these are in the TMUA or the ESAT syllabus specifically. Okay, so you have functions, limits, continuity, and all of that. Those are not in the syllabus, but the result that they produce leading to differentiation is in the syllabus. Okay, so I hope I was able to explain you that. I'll be assuming that you know the fundamentals of calculus that are expected for a student of this standard. All right, if you have any further questions, do not hesitate to put them down in the comments or join the Discord server that I have linked below. I'll try to answer your queries there. All right, so let us start. So we will assume that the function is continuous. Okay, because well, if the function is not continuous, you will not be able to find a derivative there. Okay, so if f is continuous, then this function can exist in three forms. It will be either increasing or constant or decreasing in a particular domain. See, I'm not talking about the overall function. You can have a function overall that is neither of these three. Okay, it could be periodic as well. For example, sin x. If you look into sin x from 0 to pi by 2, sin x is increasing. If you look at sin x from pi by 2 to pi, sin x is decreasing. And if you look at sin x from 0 to pi, you will observe that sin x is constant, right? It starts from 0, ends at 0. All right, so 0 to pi by 2 increasing, pi by 2 to pi decreasing, and overall 0 to pi, the average value is the 0, right? It returns to the same value. So does that mean there are no increasing or decreasing sections? No, that is not the case. So all of these theory are developed in one particular domain. Okay, I've not written it down specifically because every notation and every theoretical concept has been discussed in the official handbook. So please refer to that obviously, because that is the only source of syllabus that we have for this exam. Just make sure that you learn the notations there. But assuming that you have learned the notations, let us discuss the concepts. So a function in an interval can either be increasing, decreasing, or it will be constant. So how do we know that a function is increasing? So if a function is increasing, then if we take an input, right? So x2 and x1 are inputs. So if one of the inputs is greater than the other, then after inputting it into the function, the outputs should also follow the same hierarchy. All right. So if x2 is greater than x1, then fx2 should be greater than fx1. If that happens, then the function is known as monotonically increasing. Okay. Now in that particular domain, of course that part I have omitted. I assume that the students will know this. So in that particular domain, the function is known as monotonically increasing. Now what is the difference between monotonically increasing and just increasing? So in an increasing function, you can have greater than equals to as well. All right. So I'll leave this task to you. Find out from the internet and any of the resources that you have an example of a monotonically increasing function and an increasing function. Well, I'll give you one. E to the power x is an example of a monotonically increasing function. All right. Because if you take two different inputs of x, you will always get two different outputs from e to the power x. All right. So the same concept applies to monotonically decreasing functions as well. So we are not going to change the starting criteria. We'll keep x2 greater than x1, but for monotonically decreasing functions, we'll make it fx2 is less than fx1. All right. So the higher value will lead to a lower output value. All right. That means the function is decreasing. Okay. So an example of this would be e to the power minus x. So e to the power minus x is a monotonically decreasing function because if you take a higher value, it will lead to a smaller output. Okay. Similarly, the definition for decreasing function is fx2 is less than equals to fx1. Okay. I hope this part is understood. And now we will move on to how we test these. So to test these, we use the concept of derivatives. If the derivative of a function is greater than 0, then fx is increasing. If the derivative is less than 0, then fx is decreasing. If it is equal to 0, then either the function is constant or it has a horizontal tangent at that point. Now try to recollect, what do derivatives represent? On a graph, derivatives represent the slope of the tangent to the curve at that point, right? So if it represents the slope of the tangent and the slope is looking up, now what do I mean by up? So if the, you know from coordinate geometry, right, that if the slope of a straight line is given by y equal to mx plus c. Now if this m is greater than 0, then the slope will be positive, like it will be rising upwards until it breaches the 90-degree angle and then goes this side. If it goes this side, then it will start becoming negative and we will reach the decreasing case. But anyway, in the greater than 0 case, the slope of the tangent will be rising. So slope of the tangent rising means overall the function is also rising, right? Because if the function does not rise and the tangent tries to rise, then the tangent, instead of intersecting the function, will cross the function, and that will invalidate the definition of tangent, because a tangent is a straight line that touches a curve at exactly one point. So both of them have to travel synchronously in the same direction. So if the function goes up, the tangent has to go up, because if it did not go up, if it tried to go down, the tangent would cut it again. That is not allowed. All right. So you can visualize it this way. Remember, visualization is very important, because whenever we do high school mathematics, we usually stress more on formula and problem solving, and these competitive exams stress more on you being able to visualize those things in real world. So a gap exists, and that is why these exams feel a bit difficult. All right. Always try to work on your visualization skills via curve sketching or even drawing a graph. So a very good practice that I tell my students, especially ones that are younger or in middle school, is that whenever you encounter a graph, go into Desmos and plot it. Alright? If you plot like 50 or 60 graphs throughout your school life, you don't need to do it academically. If you are just lazing around, why not try and look into Desmos and see whatever you feel like x cube, x to the power 5, how do these graphs behave? What happens if you change a plus to minus? Alright? So if you look into all of these, you will slowly get an idea. Right? That instinct will build up. That what this graph could look like. Of course, when we study more about polynomials, their roots, how intersections work, derivatives, curve sketching, inflection points, critical points, you will have a much more rigorous idea, but that instinct will have built up. Alright? So maybe try it now. Like if you start any problems from coordinate geometry, right? Look into the polynomials that are given there, or any quadratic equation problem. Look into the polynomial there, plot it on Desmos, see how it behaves like. Alright? See if the conclusion to the problem could be drawn much more earlier if the visuals of the graph were there before you. Right? So these are some things that you can use to improve your knowledge of the graphs, right? Which are very important. Alright, so f dash x1 greater than 0 means fx is increasing at x1. That at x1 is important because you are only getting the conclusion for that particular point, because the tangent touches the curve at only one point, so your conclusion is also valid for that point. If you want to if you want to prove that a graph is always increasing in an interval, then you will either have to prove it analytically by showing that replacing x1 by any other point in the interval will not change this result, or you will have to mechanically show it for all points. Now if it is a discrete function, like takes a fixed value 1, 2, 3, 4, then it's easy. You calculate f1, f2, f3, f4, show all of them greater than 0, you know that the function is increasing. But if it's a continuous function, then you end up at a problem. Then you will have to solve it analytically. Alright? That means you will have to take any random point a or any variable that you want. Okay? Take any random point a and show that f dash a is always greater than 0 by the principles of algebra. So if that happens, then a in the domain, if it always leads to a positive result, then it becomes generalized and you know that the function is always increasing in that particular domain. Alright? So this is how we do that. The same logic applies for decreasing, so I'm not repeating it. Now imagine a function that increases. Alright? So if it increases, f dash x is greater than 0, and after some point it starts decreasing, f dash x is less than 0. So you have a scenario in which a function was increasing, and then after some hanky panky the functions start decreasing. So greater than 0 and less than 0, something must have changed in this black box, right? What changed? The amount of positive growth should have tapered off, turned to 0, and then gone to negative, right? You cannot have a situation in which it alternates, right? Plus minus, derivative goes from plus minus. No, that'll be jagged. That cannot happen. And that cannot happen because if it is jagged, then the corners it will not be differentiable there. So you are not anyway finding the derivative. Okay? So if a function changes the sign of the derivative, not the trigonometric SIN sign, SIGN sign. So if the positive or negative nature of the derivative of a function changes, it has to go via 0, right? So greater than 0, 0, less than 0, less than 0, 0, greater than 0. Now this is not always true, because you could have a vertical tangent as well. Vertical asymptote, sorry, vertical tangent is completely different. You could have a vertical asymptote as well. So if you have a vertical asymptote, then your function was increasing, it increased so much that it went as an asymptote, right? It went to infinity and then started decreasing. So in that case, you will not have f dash x greater than 0, f dash x equal to 0, and f dash x less than 0. You will have f dash x greater than 0, derivative does not exist, f dash x less than 0. Alright? So from this discussion, if you did not catch it because I did not use any illustrations, do rewind this part and listen to it again. So from this discussion, we established that for the sign of the derivatives to change, it either has to be through f dash x is equal to 0 or through a point where the derivative does not exist. Remember this. Now all of these 2 points where f dash x is 0 and f dash x does not exist are known as critical points. Alright? So usually the extrema of a function rests here. Alright? So there are 2 ways to find the critical point, just as we discussed, that either you set f dash x to 0, find the critical points, or check all the points where f dash x is d and e. Now I said or, but these are not mutually exclusive. For a function you can have both. Alright? So just to be safe, whenever you have a function, you check all the points where the critical point is 0, where the derivative is 0, those are the critical points, and you also check all the points where the derivative does not exist, maybe due to there being a vertical tangent, there due to being a discontinuity. So for this, you will need to know when a function is discontinuous. Right? Go back to your school book and make sure that you study the points where a function is not differentiable. Okay? It can be due to discontinuity, it can be due to a vertical tangent, it can be due to a corner, a cusp. There are 7 or 8 points here, if I remember correctly. So make sure you revise those points and remember those points. Although that specific chapter is not in the syllabus, the chapter on differentiability, but those rules will still apply. Well, it's a bit like addition and subtraction are not in the syllabus, but you will still have to add and subtract, right? So that's the logic behind it. So please make sure that you revise the section on differentiability, very important, and then use all those points where a function is not differentiable. That means the derivative does not exist, d and e. Okay, add them to the list of critical points as well. Okay, I have used an example here, a very simple example, mod x. So the mod x or absolute value of x, abs x, however way you write it. So absolute value of x has a corner at 0, right? So we know that whenever a function has a corner, it is not differentiable there. There are 2 cases, corners and cusps. Okay, corners are made when 2 straight lines intersect, and cusps are made when either 1 straight line and 1 curve intersect, or 2 curves intersect. Okay, so cusp and a corner, a function is not differentiable at either of these. But that does not mean that fx is equal to mod x does not have a minima, right? It has a minima, right? It does not go below 0, so that is the minimum point. Okay, so how do we calculate these in this case? So as I told you, critical point is calculated by f dash x equal to 0 and f dash x does not exist. So if f dash x equal to 0 was the only criteria, then we would not have found out this minima, because the function is not differentiable at 0. So how can we get f dash x equal to 0? That is not possible. So in this case, what we would do, we would use f dash x equal to d and e. That will be a critical point, and we check the value of the critical point. X equal to 0 is a critical point, and looking at the graph, we can see that the minima is observed from this graph. Or if the function is complicated enough such that you cannot draw the graph, then use the first derivative test, just the one that we did earlier. Check what happens if f dash x is to the left of the critical point. If it was decreasing and then starts increasing, so f dash x is less than 0 here, greater than 0 here, that means the function was decreasing, something happened, and now it is increasing. So of course, if something happened here, it could either be a critical point or a point where the function does not exist. So anyway, it bounced back, so that means that was the lowest that it could go, hence there was a minimum. Okay, I took some time explaining this. I hope you understood this, because there will be problems where you will have to make sure that you list all the critical points, not for the answer but to find the actual minima. Alright, so okay, moving on, this part is done. Now simple algorithm for finding all the critical points. Calculate f dash x, set it to 0, solve for critical points. If x is a critical point, check any point that is just less than x, so f dash x minus. If that is negative, and any point after x, if that is greater than 0, positive, then f dash x has a minima. Now how do we evaluate this? I'll just give you an example. Let's say your critical point is 5. Okay, you can take any value less than 5 to check. Always take the easier calculations. No need to take 4.99. Okay, you don't have a calculator in this exam, so why bother yourself with that? Take 0, take minus 1, anything that makes your calculation easier. Okay, something less than 5 and something more than 5. Okay, take these values, check the sign, you will understand whether it's going from negative to positive or positive to negative. But if there are multiple critical points, make sure to not cross the other. So if your critical points are 1, 5, if you take 0, that will decide only for the critical point of 1. The sign may have changed between 1 and 5. Alright, so keep this in mind as well. Alright, now that the section on critical points is done, okay, there is one more way of checking maxima or minima. If you know that the function has a second derivative, then at the critical point you could also find the second derivative. Okay, f double dash x. If f double dash x at the critical point is greater than 0, then you have a minima. If f double dash x is less than 0, then you have a maxima. If f double dash x is equal to 0, then you have no conclusion. Then you'll have to go back to the first derivative test again, or look into it via graphs. So the double derivative test is very powerful when you can calculate the second derivative easily and fast. Otherwise, stick to the first derivative method. Alright, because you will observe that in certain problems you are having to do the derivative via the division rule, and that is complicated, right? So division rule is very difficult to remember. Anyway, if you have to do that again, you are losing a bit of time. Now, in school level subjective problems, this is not an issue. You have time. But in a competitive exam, especially for TMUA, you have 3 minutes per question approximately, and in ESAT M2 you have like 1.5 minutes per question. So always go by the fastest and more efficient route. Okay, the examiner or the computer in this case will only be checking the option you marked. Nobody is going to check your rough work. Alright, so use all tips and tricks and hacks that you have of your own to reduce the calculation time, because the more you answer, the more is the probability of getting a higher score. Alright, so if you set f double dash x is equal to 0, you can solve it for inflection points. Alright, so remember, if you solve f dash x is equal to 0, you get critical points, and you get critical points from f dash x does not exist. But if you solve for f double dash x is equal to 0, you will get inflection points. What are inflection points? At inflection points, a shape change occurs. Alright, now a change in shape is not the same as increasing or decreasing. Be very clear about this. Consult your school books. There will be like a panel of 4 figures where they will explicitly tell you how an increasing function can be both concave down and concave up. So I'll just give you that example. See, a function can be increasing this way. That means it is increasing in an increasing manner. So at every point the increase is greater. It could also increase in this way. That means the increase is getting slower, but it is still increasing. So the two classical examples would be e to the power x and ln x. Plot their graphs, you will find the difference between these two. So if f double dash x, the second derivative of x, is less than 0, then you have the graph to be concave down. If f double dash x is greater than 0, then you have it to be concave upwards. So there is an illustration here. So the illustration is, at this point you have a critical point because the function has its minima, then it rises up. See, this rises up as concave up, right? Here is an inflection point. The function is still increasing, but it changes its way of increasing. So it was increasing in a concave up manner, now it is increasing in a concave down manner. But here it starts decreasing. So this is a critical point. I hope this visually shows you the difference between critical points, inflection points, and the other critical points. So maxima, inflection point, and minima. Alright, so these are the double derivative tests that I mentioned to you about. The notes are here. If you want to write something down, do make sure to pause the video and write it down. Alright, so that's about the entire theory that we had. A quick look at a few problems and then we can end this section. I can see that the video is getting longer, but hey, I'm fitting the entirety of differential calculus in one video. Please forgive me for making the video a bit longer. Alright, let's go. So this is a question from the TMUA exam itself. I don't remember which year exactly, but anyway, let's look into it. The least possible value of the gradient of the curve y is equal to 2x plus a into x minus 2a whole square at the point where x is equal to 1 as a varies. So least possible value of the gradient. See, gradient already means the slope, right? And the slope is obtained via derivatives. So the least possible value of the gradient means not only will you have to find the gradient, but also you'll have to do one more derivative. So clearly from the language you can see two derivatives have to be calculated. Well, clearly for me, it will also be clearly for you when you practice quite a lot. Alright, so first you calculate the derivative. So you calculate dy dx, you get this particular value, right? You get it in terms of a because a is a constant and you are differentiating with respect to x. Now it says at the point x equal to 1. So here you can just put x equal to 1. Alright, if you put x is equal to 1, you will get y of a to be this. Right? You just put x is equal to 1, you will get this. Now you minimize this and you should be able to get your answer. Alright, I have not marked the answer here because, well, you do it, mark your answer, and whatever answer you get will be the correct one. I think it is C, but I may be wrong. Okay, I have done this quite a few times in the class, and I think 25% sure that it's C. Alright, do check your answer. It's just minimize this with respect to a. Do dy dA, get the critical point, figure out the minimum. That will be the answer. Because I hope you understood the workflow, right? Find the gradient of the curve. Okay, this is the gradient of the curve at x is equal to 1. So you evaluate dy dx at x equal to 1. This is dy dx at x equal to 1, and then minimize it. It could have been maximized as well in maybe a different problem that would appear in some other year, but you get the general flow of the problem. Okay, fine. A few more. So the function 1 minus x divided by cube root of x squared is defined for all x. This is also a question from TMUA exams. The complete set of values for which the function is decreasing. Alright, very classic question. So for these type of weird functions, do not use the division rule. As I told you, the division rule is slightly complicated and there are chances of mistakes occurring. So just flat out divide it. So I have x to the power, this is x square cube root, right? So this is x to the power 2/3. So divide it. So you'll get fx is equal to x to the power minus 2/3 minus x to the power 1/3, right? Take the derivative. The derivative will be minus 2. So if you take the derivative and equate it to 0, you will basically get x is equal to minus 2. Right? So after setting f dash x equal to 0, I get x is equal to minus 2. So minus 2 is a critical point. Remember, I told you there are two ways of finding critical points, and you have to check both. The first one is f dash x equal to 0, for which I obtain x is equal to minus 2. Alright. The second one is the point where f dash x does not exist. We can clearly see that at x equal to 0, this thing has a, or this derivative, because there are negative powers, right? So that means these are divided, positive powers. So at x equal to 0, there will be a vertical asymptote here. So the critical points will be minus 2 and 0. So check the sign of the functions. You can draw a sign diagram, which we have learned in the section of quadratics. You can draw a sign diagram, and that will show you where the changes in f dash x occur. So I have my f dash x written. Since there are cube roots here, I checked minus 8 because the cube root of minus 8 is minus 2, and that turned out to be less than 0. So beyond minus 2, I have a negative sign. In between minus 2 and 0, I check minus 1. So that turns out to be greater than 0. Remember, I don't need the exact value of these calculations. I just need to know the sign, whether it's positive or negative. Okay. Even if you were doing this in a subjective question, you would not need to write the value. Just the sign should be enough. Now, I obtained minus 1 to be greater than 0, so this is positive. I obtained f dash 1 to be less than 0, so this is negative. So that means, what is the question? The question says decreasing. So decreasing means we'll have to figure out all the regions where f dash x is less than 0. So that means I'll select this region and that region. So less than minus 2 and greater than 0, less than equals to minus 2 and less than 0. Now at minus 2 also the function is decreasing, because this does not say monotonically decreasing, right? Remember, decreasing also had that equality in it. But we cannot put the equality on 0, but because that would make the function go to infinity, right? Vertical asymptote. So that will be gone. Alright. Very nice question. This question is very important because it shows you the importance of choosing the critical point 0. Because if you did not choose the critical point 0, you would get a wrong answer. You would get only this part, if I remember. Like one of my students made this mistake. So you will only get this part. You will not get this part. Alright? So then you will be confused and you will be like, okay, I'm not getting this, and you will move on. So not only did you waste 3-4 minutes solving this question, but also you did not get an answer. Okay, so make sure that you understand all of these. Alright, next few questions. Now, these two questions are from my book, the links of which you can find pinned in the comments or in the description. So make sure to check them out. Now, the books that are in the Amazon store right now from me just deal with the chapter wise problems. Okay, I'm working on a third book that will deal with a mixture of questions. You can look out for it. Alright, but remember, the chapter wise problems will be easy. So the questions in my book will appear easy because you only get complicated problems after you have completed the syllabus. I have structured my book in a way so that you have a chapter and 30 practice questions or 50 practice questions, so that you know the ins and outs of that chapter. Now if I'm doing chapter 1, I can make that question complicated by including some calculus stuff, but that is there in like chapter 15 or 16. I cannot do that, right? As I'm doing the book serially, I cannot include something that is coming later in the syllabus. So treat it as a practice book. The book with more difficult questions and logical based questions is under publication. I'm still typing away at night, so look out for it if you have to include more practice in your curriculum. Okay, so the second problem, the profit P in thousands of dollars generated by a manufacturing company is given by, again, a weird complicated function, right? They will always give you these weird functions. I don't think you should expect simple polynomials ever, because, well, this is a competitive exam. So where x is the number of units produced in hundreds. To achieve the maximum possible profit, how many units must the company produce? Now, this is not a polynomial function because you have a fractional power, right? If this was a polynomial function, you could have just checked f dash x is equal to 0 and that would be it. Well, this is not a polynomial function, but then again, you do not have any divisions, or you do not have any divisions. So I think p dash x is equal to 0 should solve your problem. Just ensure that you are finding out all the critical points. Check whichever is the maximum and minima. You can use the double derivative test because differentiating by power rule will be quite easy, and you will eventually find this answer. Right? The next problem deals with applications of derivatives. It says find the equation of the tangent to the curve. The curve is given and the point is given, x is equal to 1/4. So you'll have to find the equation of the tangent at this point. So quite easy. Again, follow the same procedure that we did in the TMUA problem. Just divide it. No need to use the division rule. So just divide it, and we'll end up with, if you divide x here, I'll end up with 2 minus x to the power minus 1 into x to the power half. So you can multiply it, you'll get 2x to the power half minus x to the minus half. Take the derivative, set it to 0, do all of that stuff, and you will end up with the equation of the tangent. Now the equation of the tangent is a bit different. So we will be using the first, or the 1 point form, right? If you remember the 1 point form, it was y minus y1 is equal to m into x minus x1, right? So this m, the slope, will be obtained from the derivative. This x1 that is given to you, 1/4, and this y1, you put 1/4 here. Whatever the value you get, that will be the y coordinate of that point, because the contact point, or the point of contact of the tangent to the curve is also a member of the curve itself. So the x coordinate will lie on the tangent as well as on the curve, so you can get the y coordinate of that point by putting it into the curve. Okay, so that concludes this chapter. Well, it ran a bit long, 30 minutes. No worries, I'll make sure that this video gets uploaded in 1.5x. Just go through the video. If you have any doubts, do mention it in the comments, and do check out the books that I've pinned in the description. I've gotten a bit of negative feedback for making the questions too easy, but hey, they are practice, and I'm already working on a book that has more difficult questions. So that's it. I'll hope to see you in the next one. Bye, take care.